When we talk acid-base reactions, really what we're looking at is we're looking at one of the second, basically, of the third type of metathesis reactions. And it's a need to pay attention to exactly what's going on. This goes back to what we talked about when we looked at molecular to ionic to net-ionic equations and figuring out what's really driving the reaction. In precipitate reactions, it was the precipitate. In acid-base, it's going to be the neutralization reaction or the formation of water. Now, a little history. We have acids and bases defined by three separate people. You have Arrhenius, who defined acids and bases in terms of the presence of hydrogen and the presence of hydroxide. Then you have Bronsted-Lowery, who basically defined it in terms of proton donors and proton acceptors. What this boils down to is that we have changed our definition of an acid to the presence and what happens to the hydrogen ion. If something can donate it, it's an acid. If something accepts it, it's a base. So the acid and the base is all about what we call proton donating or proton accepting. Now, there are major acids, or only 7 strong acids. Going back to what we talked about earlier, if something is a strong acid, it completely dissociates or ionizes. Dissociates, I gotta spell that out. And if it completely ionizes, that means I have H and Cl, H and Br ions all the way through. So these are our very strong acids and bases. This is important when we get into acid-base equilibrium in a few chapters, because strong acids, strong bases behave very differently than when we see strong and weak combine. Now bases, again, Arrhenius defined them as having hydroxide, but we see it more along the lines of something capable of accepting a proton, something capable of changing its composition such that if a hydrogen ion is donated from one substance, it can accept it. This means, in essence, that we can no longer just focus on whether something's a hydroxide or not. Now, when we talk strong bases, though, almost all the strong bases are hydroxide ions. So we have to expand our definition, but when we talk strong bases, complete ionization, complete dissociation, we see this happening with hydroxide ions. Now, when you look at this particle diagram, the main thing to notice is the donation and the acceptance. In this case, water is donating. Water donates to ammonia, we form the ammonium ion, and we get a hydroxide out of it. So in essence, what happens, or what creates our Bronsted-Lowery acid base, is whether we can change the substances so that this occurs. Now, imagine the reverse. If we reverse this reaction, which you'll notice you have the double arrow that tells you equilibrium, that tells you it's a reversible reaction. If we reverse this, the ammonium becomes the proton donor and the hydroxide becomes the proton acceptor. You can also argue this is what's going on when we look at water if I have a strong base, because then I have something like HCl, which will completely ionize, H plus, Cl negative, and H2O. And what I actually form is I form an H3O plus. So it would be like adding on a hydrogen ion, a hydrogen right here, and that's my hydronium ion. This is how hydrogen ion typically exists in solution. So when we look at this neutralization reaction, written out as a molecular equation, this happens to be between hydroxide and acetic acid or ethanoic acid or vinegar. We then see that also when we see a strong acid, strong base. Again, you see that both of these are molecular. Now, the big thing is to recognize what we form. We form two things. This is my salt, and then obviously I form water. So the products are always a salt and water. The salt is always going to be soluble. So when I look at this, I have HCl and NaOH. Again, I see water, and I see what I more traditionally associate as a salt. When I write it as an ionic equation, notice that we have the spectator ions have been marked out. So the driving force is simply the formation of water. And this goes back to what we talked about at the very beginning. When you are looking at any of our reactions in solution, it really does matter in terms of what's reacting, what's the driving force in the reaction, why is it occurring. And it's this formation of water that starts and runs acid-base reactions.